So this is a lecture about time abstractions. And I would say this is an advanced lecture. It builds on everything we learned so far. It builds on replicated state machines and virtual logs, on consensus, on shared memory. So everything is used in a way, but at the same time, it's also orthogonal in a way that it gives you some complementary knowledge about time. Okay, and this is something you can use off the shelf when you work with the systems, when you work with true-time API, for example, if you implement an application using Google Compute Cloud. All right, so let's talk about time. So the impression I think you have so far is that clocks are very unreliable. We cannot base any decision on clocks, on physical clocks. We can, though, work with logical time. We can work with Lamport clocks and vector clocks. But what about real time measurements? Can we do anything with that? Can we make time measurements useful for implementing properties of a real system, of a database, or a data storage, distributed data storage service? And in a way, we will seek some time invariance from physical time, from real time, whatever that is, that we can trust to create trustworthy systems. Okay. And as you know, there are many types of clocks. Okay, we're not just using here the notion of a quartz clock or an atomic clock, or we use the notion of time in general and progress over time to reason about different measurements that we can make with their low and high bounds, of course. So we will see two practical abstractions today, two categories, I would say. One is time leases. So time leases lead to shorter protocols, and they help us make stronger abstractions. They are the state of the art today when you work with consensus systems, for example, and logs, in a way that the client and server communication is abstracted. So usually, when you want to add something to a log or add a command, you talk to a leader, right? But that leader has, in a way, that leader has access to the most recent state of the system, right? Because it's a leader. But how long can you trust the leader, right? Is the leader always accurate? In a way, we can make some assumptions and say, I trust, for example, a leader for some amount of time, and that is that encapsulates the idea of time leads, right? And of course, the system cannot change leaders and do things while these leases are active. Okay. There are always downsides. So if we use time leases, as we will see later, this can bring some slowdowns. Effectively, when we do reconfiguration or a new leader needs to be elected, we still need to wait for this lease period to expire before we make this change in the system. So there are downsides, of course. On the other hand, we can really speed up reads, for example, when we work with data storage and shared memory. Then we have interval clocks, and this is a very cool idea. It was really popularized by Google Spanner, I would say, and the true-time API. The idea of interval clocks is very simple, actually, even though it might appear complicated. Is the fact that we can reason about not just point, reason about time, not just as a point in this time progress, but also as a range. And a range means that when I take a time measurement, this can be, for example, T1 here, this can be guaranteed to be in a certain deviation from real time, okay, minus plus, okay. And that means that the true time is somewhere inside here. That's where the true time is. And that means that I can wait, for example, this period in order to commit an operation, let's say, and guarantee that true time will pass this point. So you will see how this works. The way we use that is very important. We can actually guarantee linearizable operations Linearizability, you know what it is. Of course, database people nowadays use mostly snapshot isolation as a term. Snapshot isolation is a bit weaker, but of course, interval clocks can be used to offer snapshot isolation. We can talk tomorrow a bit about snapshot isolation and different types of consistency that production systems have, especially database, transactional database systems. Because as I said, the terms are a bit, they vary a lot between the distributed systems community and the data management database community. So the idea of interval clocks is also that we can make conservative time estimates. So we know that if we have a very slow clock, we can always wait up to this maximum point to know that the true time has passed this very slow clock. Or if we think that the clock is very fast, we consider this point in an interval to take decisions. This is highly used in Spanner, as I said. Also, CockroachDB is a system inspired by Spanner. Is using a notion of interval clock, even though nowadays they're switching back to loosely synchronized clocks. The idea again here is that you can get a lot of performance benefits and speed up protocols as long as the intervals that you have, the clock quality that you have is very good. So if your clocks are bad, then that can reduce the performance of the system. Okay, have this in mind in general as a overarching principle about clocks. And now we dig into these two abstractions in more detail. Okay, if you have any questions, just interrupt me. Okay, and do that with your mic. Don't write because I can't see the chat right now. So first we will talk about time leases, and I think the best motivating example is the one where we will have to implement a key value store. Okay, and we'll use some things we know already and put them in the same picture and show where the problem is and how we can solve it using time leases. So let's say we want to implement a key value store. Okay, and we know about replicated state machines. We use Raft or sequence paxos, and we support a set of commands. Okay, we have read a key or write or a value on a specific key, and we can also do, let's say, something more complicated, that is compare and swap. If we would do just reads and writes, we could just live with one of these algorithms that you learned in the shared memory chapter. But since we have something more complicated than that, which is compare and swap, then we need something stronger. And that's why we consider the use of replicated state machines. The way key value stores are created is that, first of all, they support some form of data parallelism. So they allow you to shard the key space that you can write values on. And for each shard, you can run your specific dedicated instance of a replicated state machine. Okay. Now compare and swap. What is this? Compare and swap is a more complex operation than just a write, but in fact it has the same effect as a write. So what it does is that it has three parameters. It has a key, a value that is the expected value that we expect to read when we access the store, and also a value that we want to write. So what the system does, if you do compare and swap with these parameters, is that it will go and write this new value as long as the expected value is matching, and then it will return the old value. So in a way, we compare two values. We see if if the existing value is what we expect. If it is, then it's going and replacing that value with a new value and returning back the expected value. So that's how it works. If it's not matching, if the VEX doesn't match our existing value for that key, then the write does not complete, basically. So we just get back the existing value. So effectively, we need a replicate state machine to implement compare and swap. And that means we need to execute one of these leader-based sequence Paxos algorithms, or multi-Paxos, but preferably it's better to execute a leader-based sequence Paxos algorithm. So Raft or OmniPaxos, for example. And let's say we have three replicas, P1, P2, and P3, and each of them is acting both as a proposer, acceptor, and learner. So a client basically can connect to any of these instances of our data store and issue any of these three commands, basically. So here we have a set of, we have a quorum, these three processes that run our sequence Paxos algorithm, and we have a set of clients that surround these instances, and they communicate with them in an arbitrary way. So any instance will try to connect to a proposer and try to issue a read, write, or compare and swap operation. So we can have an arbitrary number of clients, okay? And we assume that the network at this point is stable, and at this point, P1 is a leader, because this is a leader-based protocol. So let's say client P4 wants to execute a command, and what it does first is that it just sends a request. We denote this as 1 with sequence number 1 to the leader here, that's P1. Then what the leader does is that, it's proposing this command to the Paxos, the underlying Paxos instance, if it's Paxos. And that means that it needs to send accept messages to all these replicas. We send accepts because we don't need to do a prepare at this point. We are running sequence Paxos, and P1 is the current leader. So that's fine. We do another round, basically, of messages to all of the processing this quorum and trying to collect the majority of votes. Then we have a response. That's a response. It's coming back from the accept request. That's the accept acknowledgement, and that is now going to commit basically the operation in the store. Okay, and what comes next is that, okay, P1 has collected the majority of accept acknowledgements, and now it's ready to say back to the client, this is decided. Okay, and of course to all the replicas, because we run the decider, the learner code also in every process here. And this is communicated back to the client as a response of the operation that was issued, right? And you see here that we have a lot of steps. So for each read or write or compare and swap, we have to do a lot of steps, of communication steps, right? So how can we speed up this process? First of all, reads. Reads are very easy to speed up. Why? Because most probably we could just get the latest state already from the leader, right? If P1, which is the current leader, stores the entire state of our log and the replicated store, you can read that state directly and respond to that read operation back to P4. Okay. However, partitions can happen, and that's a big problem in distributed systems, as you know. So network partition means that this cut of the network, as you see here in the picture, will occur, and then servers, and maybe clients too, but servers will be isolated from each other. So in this case, P1 is isolated from P2 and P3. And that's kind of problematic, right? It's problematic because now another server might be elected as a leader. So P2, let's say, is elected as a leader, and P1 at this point cannot learn about this, right? P1 is totally unaware because it's disconnected through the network partition, right? So what happens now? So another client tries to send a write operation. So basically write this value for key X to P2, is the current leader, and P2 communicates with P3 and commits the write operation. So basically we have a new value written in the store, but of course this is restricted to these two nodes here, because those are in their own partition, and they have their own leader, which is P2. So after this request, let's say this operation is complete, P1 is still lagging behind. and my thing that still is the leader actually. So after this, P1 gets a read operation from P4, same as before. And since P1 is unaware of the split, and it can, return, as we said, like using this optimization, we can return back to the requester, which is P4. Then we see a clear violation of linearizability, right? Why do we have this violation? Because another operation that wrote to that key completed before this read, and it wrote a new value, right? The operation that was stored here in these two nodes through P2. But of course, this is not communicated to P1. P1 thinks it's the leader, but it has an old value of that, an old state for X. And that is bad because basically, if somehow, let's say, these guys too can communicate with each other, then P9 can say to P4, look, I send you some money to your bank account. Please go and buy this present. And then P4 will go and buy something with no money, basically, because the information it gets here is totally outdated. So this is really bad. Okay, linearizability is very important to not violate in these types of systems. So P1, as evidently cannot respond with its current state. So we cannot do this optimization assuming no leadership, because we might end up in a partition, or P1 might die also, right? So is there some way to avoid this? So the strawman attempt here would be to let P2 to enforce P2 to communicate with P1 before P2 can become leader, right? So basically let the leaders pass the baton, basically. But of course, that's a bit stupid because at this point, P1 might be dead, right? So P2 might try and retry to become a leader and update the old leader, but this will not work out because either P1 is totally disconnected or P1 is dead. And that is bad. So in that case, we can still do this optimization by using leader leases. And effectively, what this implements is this idea of having disjoint leader elections through time. So if you look at this picture, you can see what I mean. So at any point in time, let's say T2 here, we have only one leader, basically. And once this, from T1 to 2, this period expires, then we start, another period where another leader is guaranteed to be considered leader by everyone. Okay, and that can be done by using leases, by using some kind of special promise that, look, I'm not going to trust anybody else in the system as a leader for that amount of time. And each process does this, right? And this is the idea of a lease. So how does it work? A proposer, P wants to be a leader, so it sends a request to all the acceptors. Then an acceptor can give back a time-based leader lease to that P process that is lasting for some amount of time, let's say 10 seconds, okay? So now if a proposer gets a leases for a majority of acceptors, then it can hold this lease on that group and become the leader, right? For at least 10 seconds, right? So this is a period that it needs to wait, and in that time, until the first acceptor lease expires that we received, then the proposer knows that no other proposer can claim the lease from that group of acceptors, right? Because every acceptor promised that, look, I'm not going to trust anybody else for this amount of time. So that means also that the leader that holds the lease can safely respond to reads from its local state, right? Because it's always up to date, since everybody is trusting only that leader, and that leader basically decides about everything, so it knows about everything, right? So we avoid this extra communication step to do reads, basically, and access state. So that's cool, right? So here you see the how this will work. So P takes a lease, and of course it waits for amount of time while Q is also waiting for that same amount of time, 10 seconds, right? Since it receives that lease request. And effectively, this is a period where nobody can really try to convince Q that it's a new leader. Now, this leader list can be integrated with Paxos messages. So same as before, an acceptor Q joins at round N by sending a promise, right, to in response to a prepare of a ballot number N, and promises to not accept also any proposals in lower rounds. That's the vanilla Paxos. But in addition, we add one more constraint, one more invariant. So the promises something more, and that is not to join a higher round until this time has elapsed. So a promise is a stronger form of a promise, right? We promise not to accept proposals in lower rounds. At the same time, we don't accept even higher round proposals until this time has passed. Okay, I hope this is clear. So if a proposer gets promises from a majority, then that proposer knows for sure that no other proposer can get majority of promises during that period of 10 seconds. So that's simple, right? But where's the catch? Where's there must be something challenging here. So note that we are only talking about physical time intervals and not about absolute clock values. So we have to take two issues in account. There are two problems, right? Two very uncertain delays. One is the network asynchrony. So when we send a lease or the network, or when we send, until we grant it, basically on the other side, there might be an arbitrary amount of time. It might even be that by the time we receive the lease has expired. So how do we know that this doesn't happen? Then we also have the very, very low level problem that is the clock drift. So if you take the clock of the proposer and the clock of an acceptor, it's not guaranteed that these two clocks are progressing over time in the same speed. So it might be that one of the clocks is running faster, is doing like more ticks than the other clock, because clocks are not the same. So there are external factors that affect the performance of a hardware clock, of a physical clock, especially when we're talking about quartz-based clocks, right? So just to depict what I mean, first of all, by network asynchrony. So here you see at time t0, P is sending a prepare request, right? Asking for a release, basically, to get back a release. Then the acceptor Q receives that at time 1, and then sends back a promise with a lease. And that is received at time 2. So how long does P hold the lease now? So P cannot really wait until it receives the majority of promises and then count that amount of, that duration of time, because it might be that, there was no network delay. Okay, so it might mean that the acceptor now has already started counting these 10 seconds. So it could start here, right? So this is a bit problematic. And that's why we have to be conservative at the proposer side and hold the lease from this time that we sent, the request, the prepare request, plus 10 seconds, right? So we have to wait this period and be conservative that, we are not holding more than that, because that's the minimum possible time that an acceptor might wait for a lease. We don't want to wait more than that. We don't want to claim leadership more than that, because if we do that, then another proposer might take the lease while we don't know it, right, from the acceptor. And that's problematic because then we might not have the latest state. Then the acceptor waits from the point, it receives a prepare request and starts measuring time, basically. Even at the point it sends back the lease to the proposer. But then we have the clock drift problem also. So, okay, this solves the network asynchrony problem, right? So we basically we basically use delays that are the most conservative, so that we don't violate linearizability, right? And we don't violate correctness. So when it comes to clock drift now, we need to first understand why do we have this clock drift? Okay, what is this? And we have described it a bit more formally so that you understand what I mean. So a clock at a process PI is, first of all, what we call a monotonically increasing function from real time to some value. Okay, so you can think of time in a local clock and a real time. Okay, so basically this always points to some time here, right? It's like a function that is always increasing over time. Okay, as long as you ask for the current time one after the other, right? You always get a new time that's higher. Now the clock has to be associated with what we call this variable, and this is modeled as a function. This is a function basically from real times to clock times. So what is real time anyway? So this is kind of philosophical, right? We have a way of measuring real time, and that is a standard. So there's this UTC standard that is basically the well-agreed coordinated universal time. And this standard describes how we measure time universally, right? In any device, in every country, every system, and so on. And the unit of time is basically a measurement of what is a second, millisecond, nanosecond. What does it mean really? If you take two measurements, how much time has it passed? And so, like if you look on the physics side, there is a way to measure that, and this is like a well understood, well agreed way to measure this period of 1 second, for example. So the second is, for example, the duration of this very big number of periods. So periods as in, you can think of something that's oscillating of the radiation that corresponds to the transition between the two hyperfine levels of the ground state of cesium. So we have like some kind of special like atom here that we use to make these measurements. And this is like this is also the way we nowadays build atomic clocks. So there are very expensive clocks that follow this standard. Okay. Now there's no perfect clock. Okay, and what I mean by that is that there's no even atomic clock that doesn't drift over time. Okay, at all. So everything drifts, and that's why we have many atomic clocks in the world to derive what's the passing of time. Okay, what is 1 second? We don't use just one atomic clock, we use many of them. And of course, we don't use other inaccurate clocks, right? So we use good clocks. So these good clocks are based on this cesium 133 atom, and they basically measure the activity of the atom, and which is very consistent, by the way, to derive this set of periods that say, okay, this is basically 1 second. Okay, so then how do we build clocks? Okay, so the clock is not just a measurement of an oscillation, it's also a counter. So it's basically two things. We have an oscillator that is measuring some kind of frequent activity, it's hardware. And then we have a counter that is actually counting the passing of time. How many of these frequencies or batch of frequencies we measure over time. Once we see 1 million, then we increase the counter, for example. So that's how even your laptops or your desktops clocks are set up, right? So even a quartz clock, it has an oscillator and counter, these two hardware components. And as I said, the oscillator frequency is not completely stable. Even for really accurate clocks, there's always some form of external factors, environmental conditions, the temperature, the moon phase, everything, magnetic fields, everything affects a little bit these measurements, these frequencies, and that means that over time we have some form of a drift. Also, clocks get bad over time. So if we use the same clock now and in 30 years, there will be more drift shown in 30 years. Okay. But then there's one thing that is very nice in this craziness of how clocks work, and that is that the manufacturer can certify that there's a nominal frequency and an error bound. Okay, that is pretty cool because we can use this as a basic principle to make useful guarantees maybe. So error bounds are very nice. Now the clock rate specifies how much the clock is increments each second at real time. So for example, the counter increment by nominally 1 million ticks per second with an error bounded by plus minus 100 ticks per second. That's the drift. And then what we do is that we normalize the clock rate such that we say 1 second is the nominal rate, and the error is given by a variable that we call rho. Okay, and there's this formula that we use also in distributed systems to write down these bounds. Okay, so basically, if the error is given by rho, then the deviation of the clock time to real time is also bounded by these two ends, which is 1 minus rho if your clock is very fast, or 1 plus rho if the clock is very slow. Okay, I hope that's clear. So in our example, we also normalize rho like this and say, this is the standard rho value. Now the clock drift is the accumulated effect of a clock rate that deviates from real time. And ideally, if we have no drift, that means that the duration of the clock is equal to the duration of real time, and that is basically 1, right? So if we see this picture here, the perfect clock without any drift would be that line here that has no drift basically, and the clock is effectively measuring real time. But of course, we can, in reality, we don't have a single line, but we have this kind of a cone to base our assumptions about our clocks. This cone here that shows basically the upper and the low bounds of our clock with drift over time. And one thing you can notice here is that over time, this cone, this distance here is increasing, right? So the more time is passing on, the more diverse values we might see in our clocks. So let's go back in our protocol now and try to use leases with drift into account, taking drift into account. So first we have the proposer logic, and here we have to reason about what happens if proposer uses clock time instead of real time without any compensation. So if the clock runs faster, okay, then safety cannot be violated in the proposer logic of the lease. Why? Because in the worst case, what can happen is that the proposer might believe that its lease is expired sooner than it actually did, right? So it might just release its lease and say to the client, look, I'm not the leader anymore. You cannot trust me. Try to find the current leader. And that is fine, because then we're not just giving an invalidated, an old value at any case, right? Because a client would always get a lease from and talk to a leader that is actually the widely considered leader. Okay, so we cannot violate safety. Now, if the clock runs slower at the proposer side than real time, then it might happen that the proposer believes that it holds a lease for a longer period, right? So it might think that it's a leader longer than the acceptors think that this guy is a leader. And that's bad, because then the acceptors might consider someone else a leader, right? And then in that case, the values that we read from that old leader will be inconsistent with the current state of the system. That is bad because it violates linearizability. Okay. So what do we do? We have to be conservative here. So a proposer must compensate by assuming that its clock is running as slow as possible. Okay, that's the worst case. So that means that this is what we think is the current value of the time using this very very low drift, basically. So to compensate, let's say that we take a lease for 10 seconds. Okay, what do these 10 seconds mean? How do we measure them at the proposer side? Where we use this formula here to and add 10 in for dt to find basically how long we should wait. Okay, and that is basically 10 times 1 minus rho. Okay, which is basically the conservative estimate of what's the shortest time we can wait that guarantees that we don't violate linearizability. At the acceptor side, the acceptor also uses a clock and measures time, because it has to basically put this lease into effect, right? When it promises that it's not going to accept any request for an X number of seconds, then this X number of seconds needs to be measured in a way that doesn't violate correctness and accuracy, right? So what do we do here? So at the acceptor side, we consider, first of all, what happens if the clock runs faster than real time. In that case, the acceptor might believe that its promise expired too soon, and in that case, that means that it might give the new lease early, and that can violate safety, right? So it's kind of the opposite on the acceptor side, because if we under speculate, then means that we might give someone else the right to be the leader, right? And that is bad, because if we give the lease to someone else, then the old leader becomes invalidated for a bad reason, because the real time doesn't follow this speculation. And that is when the clock runs faster. And then, of course, when the clock runs slower, this is still fine. It means basically that the acceptor might wait for a longer amount of time to give the lease to someone else, basically to give a new promise to someone else. So what should we aim for here? Again, it's the same conservative logic, right? So this acceptor. So basically, in this case, the acceptor must assume that its clock is running as fast as possible. Okay, so that we basically not rush to give the lease to someone else, but wait a bit longer just to make sure that we don't violate linearizability. And that means that we use this formula, 1 plus rho, to compute and measure the amount of time we need to wait until the lease is expired. So let's say again, the lease has a 10-second duration. In that case, then we wait until the current time that has passed is 10 times 1 plus rho. Okay, and that's the duration at the acceptor side. Now, if you look back to the protocol after we make these changes, the acceptors have it's a very minimal change, I would say. The acceptors have a new state variable that is the time they promise, and the clock time when they gave a last promise. So if acceptor PJ gets prepare at time t, then instantly it needs to start measuring time, right, from this point in time, but only if the invariants hold. And what are the invariants? First of all, we have this, that is the Paxos invariant, okay? That is a promise of Paxos, we don't change that, but we also change this invariant, that is the lease invariant, okay? If someone else holds the lease right now, we return like a NUC in this case. So we can reject prepare phases as long as we have promised to hold the lease for someone else. And we wait until this time has elapsed, and then we can give the lease to someone else. We can accept, we can promise to a prepare request. At the proposer side, the proposer has we need to keep track of some timestamps. So we have the TL with the new timestamp we need to keep, and TL is basically the time we sent a prepare statement, the time we try to acquire a lease. Why is this timestamp? It's this timestamp because if we assume that there's no network delays, that might be the time that the acceptor starts counting time, right? If it instantly receives that prepare request, the acceptor might start measuring time. So we need to consider even this conservatively and say TL is the time we issue a prepare request. Now, if the proposer gets promise from a majority, it means that now it can consider itself a leader until 10 seconds after TL, which is the issuing time of the prepare, has passed. And as long, remember that we always do a conservative estimate. So we use 1 minus rho as a clock drift. And we can respond to reads directly from the local state until our local clock has passed this period, right? And this is how it looks. So at time 0, P1 acquires this timestamp, which is the time it sends a prepare statement, the prepare request. The prepare request is received by P2 and also P1. And P2 at this point acquires a timestamp that is a timestamp it promises to hold the lease. And then P2 holds the lease for this period of time, right? So P2 will hold the lease until this time has passed. It's based on this estimate. The P1 on the other side will receive at this point the majority of promises, and it means that it will now wait for wait to hold the lease until this time has passed. Okay, so P1 will wait until T3, and P2 will wait until time T4. So one is over speculating, the other is under speculating, just to ensure that correctness is not violated. Okay, and that's why P1 waits from the time it issues a prepare, and P2 waits instantly by the time it receives the prepare request and holds the lease. Okay. And of course, during that time, P2, if it receives, for example, a prepare request from P3 or any other process, then it's going to reject it. Why? Because it holds the lease for this guy here, P1. Finally, one small optimization we can consider is, of course, you might say, why do we need to renew the lease and wait for this period to elapse? We don't need to do that. We can always, if we have a stable leader, we can always assume that the leader can proactively, before the period of the lease expires, go and ask for an extension of the lease. We can do that, and it doesn't violate correctness because every acceptor will also renew the lease at the time it gets the new extension prepare request from the stable leader. Okay, and that's a good idea because we don't need to wait this additional time period where we need to re-elect a new lease and acquire a new lease basically. This can happen in an overlapping fashion with the current lease. Okay, so basically the change we need to make the protocol is that we allow the current leader to extend the lease, but not other processes to request a new lease during the lease time. Okay, so that's the first topic. Do we have any questions so far? So that is simple. It's something very simple. It's something you use in practice for any type of client-server communication. It optimizes for fast reads. And next, after the break, we will see something a bit more advanced. Okay, and we will end up considering the repercussions of interval clocks tomorrow at our final lecture, where we overview database systems, distributed database systems. Okay, so now we're entering the more interesting part, and that is interval clocks. As I said, this has been used, and it's under use daily by the the world's biggest geo-replicated databases like Spanner. And as a motivating example, we will use our shared memory algorithms, especially the read impose write consult majority. Okay, and just to give you a refresher, we had a set of atomic registers, right? And the registers supported two types of operations, reads and writes. So can either write a value to a register or read its current value. And we defined linearizability, right, in this setting. And we said that the shared memory system is linearizable if you have two operations, O1, O2, and O1 returns before O2 is invoked, then O1 must be ordered before O2, right? And this is very important. If we are able to satisfy that, then we know that everything can be ordered, linearized across these processes. Okay, all these operations. And of course, just to remind you, linearizability is stronger than what we call sequential consistency, where sequential consistency corresponds only to the view that a single process has about the system and its registers. So if you can place all the operations in a sequence from the perspective of a process, then you have sequential consistency. If you can do this globally across processes, then we're talking about linearizability. And that's the strongest consistency level we can have in the setting of distributed registers. Linearizability, when it comes to transactions in databases, is even stronger because instead of one operation, we can have sets of operations. And we want to satisfy linearizability using sets of operations. Okay, so let's say multiple reads and writes across different objects in a single operation have to be ordered, with other sets of operations that we call transactions. But here in the setting, okay, we in distributed registers we talk about only one register, okay, and we say operations on these registers have to be linearizable. So read and write operations, basically. I hope if you have any questions, just interrupt me. And we talked about this algorithm in this course that is called the read impose write consult majority. The algorithm has two round trips to a majority of processes for both read and write operations. So we have to do for any type of object access, either reads or writes, we have to do two round trips with a majority. So let's say P1 invokes a read, then it has a first query phase that tries to extract from majority of processes the maximum round number, okay, and a value. And of course, then it tries to, in the second round here, it tries to impose that number that it read, that value, to, again, a majority of processes. And why we do that? Because a read, we don't want to do stale reads. We want to impose our reads in a way that every subsequent, every operation that comes after that read will see what this read has seen. Okay, so in a sense, we sacrifice protocol rounds, we sacrifice writes, distributed writes, in order to enforce some sort of ordering of the global operations of the system. Okay, so we instrument this global ordering by imposing reads and writes on a majority of processes. Okay, that's what this algorithm is doing. And this works as long as we have just reads and writes. It doesn't work as it is if we do more complex things like multiple operations on multiple objects at the same time, right? So it doesn't work for transactions, but it works for single, reads and writes that we do on objects. Every operation that comes for writes as well, we have again 2 rounds: a query round that gets the current maximum ballot number, current round number, and the current value. But then we need to enforce our new value and write it in a new round. That is the update phase. So both of these protocols have, in a sense, an update phase. Okay, a query phase and update phase of these operations. And we say that an operation terminates when we actually go and where is it? When we go and receive all the acknowledgements from a majority. Okay, so this is the point where we notify the clients and whoever is interacting with the system that this operation is complete. And this is also the time that we say these operations are linearized in the global sequence of operations over time. So a phase again is one round trip of communication to the majority of replicas, and we refer to the first phase as a query phase, the second phase as an update phase. A read operation invokes a read operation OR. In the query phase, its process responds with the highest timestamp value, and this process now picks the highest timestamp value pair received in the query phase, like TS, V, and then before returning value V, PI performs an update phase. Okay, so before we notify the client, here's the value, we first need to notify everybody else, here's the value I read. And this way, any operation invoked after OR is completed, is guaranteed to see a timestamp greater than or equal to TS. So we enforce ordering. How can we optimize a read operation? There's not much we can do, right? Because we might read something that is not really complete yet. We always pick what we say the maximum, right? We pick the latest that we read from majority. But this doesn't mean that there exists a majority that knows this highest latest value. Okay, there's no guarantee that the majority exists. If a majority exists and we happen to get a response from that majority, then we can apply an optimization that basically skips the update phase. Okay, so we don't need to write. We don't need to update everybody else that here's the value, the latest value I found. We know that this value is already communicated to a majority of processes. And in that case, we don't need to try again. We just return the client. So if we do a query and all of the answers in the majority have the latest value pair, timestamp value pair, then we just instantly return. Okay, and that's the only optimization we can do when we do reads. What about writes? So a process invokes a write operation, OW, and in the query phase, again, its process responds with the highest timestamp value received. Okay, and after the query phase, this process picks a unique timestamp higher than all the ones that it read in the set, because we always need to offer linearizability. It means that when we write, we need to bump the timestamp of the operation, right? Or the timestamp in this case is the round number. And whoever writes needs to read what's the current maximum and try to bump this up to a higher, even higher number to pass the write consult majority phase. And so it does an update, and everybody's storing the timestamp value if it's greater than the one they have already. So it might happen that in this phase, the write is older than another write that is concurrently happening. So how can we optimize writes? Think of the following. So if processes have access to clocks, to atomic clocks, right? It would be possible to skip the query phase Why? Because we could substitute the round number with the clock value. So what I mean by that? So process PI is invoking a write operation and instead picks the current measurement of its local clock, which happens to be an atomic clock. And this is we denote like this. Okay, so the timestamp is basically the value of the clock at process I, and we have also the round number in case of clocks that have the same measurement. You can always order them by process ID. Now we use pairs, and this would actually work, and this would ensure ordering, global ordering, linearizable order of operations, if and only if the clocks were somewhat synchronized. Okay, and this is a notion of interval clocks that we use to offer this idea of using real time to mark operations with linearizable order timestamps. And of course, we commit each operation. We need to commit each operation at the time we acquire these atomic clock timestamps. And this means that we can take these operations and place them in our in our sequence, global sequence of operations of our distributed system, and have a predetermined linearizable order of every write operation. Okay, so that's very important. And let's see, what do I mean by clock synchronization? Because that's a heavy topic. So formally speaking, let's say we have two clocks, clock Ci and clock Cj, and we say that those clocks are delta synchronized if for all times t, the difference of these clocks, the absolute difference of these clocks, is bounded by some constant delta. Okay, so we know that these two clocks will give you a measurement that does not vary from each other by this delta constant here number. So in a sense, we bound the level of asynchrony we can have across our processing in a distributed system. And we usually say that Ci and Cj are synchronized to within 10 milliseconds, for example, and we mean that delta is 10 milliseconds. Now, if delta is 0, then we say that these two clocks are perfectly synchronized clocks. It means that they don't deviate. They just give you exactly the same measurement at the same time. Then we also have this notion of loosely synchronized clocks that says that, okay, we can do a best effort synchronization of two clocks in the system, but we give no guarantees. And in practice, this is what most systems do, and it's pretty bad because we cannot take we cannot extract any invariant. We cannot make any property out of it because loosely synchronized means not synchronized. It means that we cannot put any bound and use it for reasoning about the actions that are happening in the system. It might be that this bound can change over time. So loosely synchronized, in effect, is not synchronized. Now, if we now substitute, if we say that clocks are perfectly synchronized, okay, then we can prove that our registers would satisfy linearizability. So if we timestamp all our system events with values measurements that we get from perfectly synchronized clocks, then everything will be ordered, right? So let's say operation 1 is a read or write, it doesn't matter, and operation 2 is a read operation. But with the same argument as before, O1 is ordered before O2, right? Because the timestamp of O1 would be lower than the timestamp of O2. If O1 is a write or O2 is a write, then O is completed before O2 is invoked, right? Because the timestamp of O1 is lower than timestamp O2, and the value written by O1 is overridden by value of O2. And the same, so when it comes to read and write operations, we know that the same invariant holds. Since there is a previous write, there's a first write, the initial write in the worst case, that initialized this object, let's say, and this has a timestamp. And of course, this timestamp, we can say that it's the same timestamp adopted by the read operation, okay? Because the read operation adopts and it takes queries and gets the latest timestamp written, right, for that object. So the latest write, basically. And it's equivalent to the latest write. So it's the same as write to write dependency. And of course, that's lower than the timestamp we acquire on a subsequent operation 2. Okay, so everything is linearizable since there is this notion of global atomic time as long as all clocks are perfectly synchronized. Writes and often reads take one round trip and correctness is guaranteed. Now, if clocks are loosely synchronized, then registers don't satisfy linearizability. Because if, let's say we have an operation 1 that's a write, completes before operation 2, that's another write, is invoked, then the timestamp of O1 might still be greater than the timestamp picked by O2. Okay, so it means that we have an operation here, and of course we say this is the time of O1, okay, and in another process we finish another write operation O2. Well, there's no guarantee that TO1 is lower than TO2. There's no guarantee when we talk about loosely synchronized clocks, okay, because these are not synchronized. So it might mean that the time here, this P2 might think that it's very, back in time. So there's not really any sort of common measurement of time. And that means that we cannot linearize things. We just get arbitrary round numbers to mark our operations. Databases that are used in productions like Cassandra DB is actually based on loosely synchronized clocks. And since we don't have this way to timestamp operations in a linearizable fashion, then there's no guarantee that Cassandra will give you linearizability, right? That is bad if you want linearizability, of course. If you don't care about that, then it's fine. If you care about sequential consistency, then you can even go with Lamport clocks. Because if you remember, Lamport clocks mark and order things that are causally related, right? Of course, when we talk about linearizability, there's no necessarily a causal dependency that is visible in the system. Because remember that things are distributed. When we talk about linearizability, we talk about global ordering. And you can think of, the previous example where we had a process talking to, one leader, another process talking to another leader, clients. These two clients might be related to each other, might discuss what they see in the system, and they might see things that are totally inconsistent, right? So one can see an update, the other might not see this update and run an operation after the first one while not seeing the effect of the first one, right? So it's not guaranteed in a non-linearizable system that we will see globally a correct sequence, a consistent sequence of operations. Okay, and Lamport clocks are useful if we are only interested into sequential consistency, because that is something we can use. We can use Lamport clocks to mark with sequence numbers the operations happening locally, let's say initiated locally in the process, or accessed locally by a process. But we cannot do this at a global level, okay, because most of the things happen concurrently. Now, of course, the best choice here would be to just go with perfectly synchronized clocks. Okay, so we have access to perfectly synchronized clocks. We can timestamp things globally in linearizable fashion. We don't have any deviation in the measurements of the timestamps we acquire from the synchronized clocks. And that means that everything can be placed in a single sequence in a single line of operations. So we are fine, right? No, we're not fine, because perfectly synchronized clocks are not possible to implement. Okay, this is nature. We cannot really, no matter how many atomic clocks we combine, we cannot build what is called a perfectly synchronized clock. Okay, so synchronized clocks across an asynchronous network even adds more uncertainty. So even if we have access to atomic clocks and they are synchronized, we still need to access the network to talk with these clocks. Okay, and that means that we have one level of uncertainty introduced when we try to, acquire these measurements. Even transferring these measurements introduce another level of uncertainty, and that means we cannot have this abstraction. Okay, but there's a practical clock, and that's the one I want you to remember from this lecture. That's interval clocks. So an interval clock, as a process I, reads at a time t not a single value, that's a timestamp, but a pair of values, a low and a high. So it's basically a range, okay, a range of times. And what does this range mean? So the low means that basically this is the smallest timestamp, the smallest time that might be the real time, and this is the highest the highest value of what we think is the real time. So this clock gives us a range, and the real time can be anywhere in this range, basically. But we know that it is within these bounds. We know that real time is within these bounds when we take this measurement. And that's the interval clock. That's very, very cool. And it's also very practical and easy to implement. Even when you don't have the perfect atomic clock, you can always implement this even at home, okay? Because this is based on a speculation, okay, maybe speculation, but a safe speculation about what is the error that you have in your clock, basically, okay, the level of uncertainty. And as I said, the correct time t, the correct time is the real time, the global time, is always guaranteed to be in this interval, within this interval, which is low and high of the measurement that we get when we try to acquire this interval clock time. Now, I talked about uncertainty. Uncertainty means that the more you are uncertain about the accuracy of the clock, the longest the width of the interval. Okay, so that means that if I have a very synchronized clock, the width can be short. If I don't synchronize often with GPS time or NTP, and I don't have an accurate physical clock, then the width can grow more, right? Because then I have more uncertainty about what's the accurate measurement of time, right? So it can be anything between within this range. And this is actually, in fact, the strongest guarantee that we can implement in practice, right? Two wide intervals mean that we can use this to reason in algorithms, and a very wide interval would mean that we would have to wait in our protocols more to respect this, higher window of error. If the interval is small, then this can actually hurt correctness. So if we basically under speculate about the error, then that might hurt the correctness of the protocol. If we over speculate and we are more like conservative about the error estimates and the uncertainty, then we don't violate correctness. That's guaranteed, but we might violate some performance SLOs, let's say, in our system. A perfect example of clock synchronization is Spanner. And I would say not Spanner, but the True Time service at Google. Spanner is a database that is a sharded, geo-replicated, high-performance, unlimited scalability database built by Google, and that is using a True Time service to timestamp all the operations that are happening across these shards. And in a way speed up reads, because because in a way we have these points of linearization that we make based on time intervals. The true time service if you see the API, looks like this. So you can always acquire the current true time, and that gives you basically a low and a high range. So it's exactly what we said now. And of course, the system does not give you a consistent interval over time, but it gives you, as I said, a conservative interval. Now, the way this works, we might see this more in detail tomorrow, but just to give you a brief overview of Spanner. So first of all, Spanner distributes the data by shards. So if we have, if you can have millions of keys, then we split that key space into different partitions. These partitions are replicated in each data center. So we have, let's say, one in Europe, one in the US, one in the US, and one, like, say, in Russia that is disconnected now. And then each of these geo partitions will have access to its own high performance atomic clock. Okay, so atomic clocks have very small drift, I would say. That's the main feature of these atomic clocks. They are very expensive. Sometimes depends on the quality of the atomic clock, because they're doing a lot of measurements at the atomic level to give you a good estimation of real time. But of course, they always drift. If you take a lot of atomic clocks, they always drift a little bit. And for that purpose, they also combine them with GPS clocks. So they effectively synchronize these atomic clocks every a few minutes, maybe, or hours. And of course, at the same time, synchronize the clocks of the respective servers in its shard that they have using the true time service. And this is interesting because what happens is that if you see the estimates, we have conservative estimates of let's say uncertainty, and at some point we do like a synchronization, and this drops down to a small level of uncertainty, let's say 1 nanosecond of accuracy. And of course that increases over time. We synchronize and that drops back. So the intervals are dynamic in a sense. Okay, the intervals depend on how often all these clocks synchronize with each other. Okay, and these combinations of clocks communicate to via NDP, GPS to synchronize and basically fix their counters. Okay, this is a very cool system. There are some concepts here that stop me from explaining you everything. For example, we have two-phase commit. We haven't talked about two-phase commit yet, so we are going to briefly talk about this tomorrow. But what is interesting is that for each shard here that you see, so its data shard has its own group, Paxos group, that's running Paxos to decide, leader-based Paxos to decide on operations, write operations that are applied in elements of those shards. And that is happening across data centers. In addition to two-phase commit, there's also two-phase locking for transactions. So in a way, Spanner is like locking objects so that we make sure that, first of all, we don't have deadlocks, and also transactions manage to acquire all the locks they need to write in their objects and then release them for another transaction to use them. And that is happening in a two-phase protocol that is committing those lock acquire operations. In any case, what you need to remember at this point is that Google Spanner provides very fast reads, and it does so by utilizing interval clocks. Interval clocks, in this case, are very accurate and very provide a very short error bound based on the hardware tech that Google owns, basically. Okay, so it's a good combination of software principles and hardware performance that gives Google this ability to create this very large scale consistent database with transaction support. So it's a very cool system, I would say. Now, let's go back to intervals, okay, and see what type of invariants and guarantees we can extract. So the interval values of a set of clocks really at the same time are guaranteed to overlap in the correct time. So what I mean by that, let's say at time t, this is real time, we try to get a value of a clock, okay, C1. And that gives us this range, this orange range of low and high bounds, okay. If at the same time we acquire the time of the interval clock of another process, let's say C2, we still get an interval. That's a different interval, but what is guaranteed is that these two intervals actually overlap because they are acquired the same point in time. Okay, and that means that there are two different intervals, but overlapping on the same point of reference here. Okay, and we can get even more intervals at that time using different clocks, basically, and even the same clock at different time. In the case of spanner, can if we try out the clock after it's synchronized with the GPS servers, then it might be that the interval is actually very shorter now. So this can change over time. Now there are a few nice invariants that we get from interval clocks, and that's what we use to make linearizability possible. So let's say a clock I reads at time 1, clock J reads at time 2, and these two times are ordered. Like, so we first acquire a read measurement on clock I, and then we take a measurement on clock J. Okay, and by then I mean afterwards in real time. So we know these two invariants already. We know that the time 1 will be somewhere between this low and high bound. And then, of course, time 2 will have its own low and high bounds. Now we know that T1 is less than T2, right? And that implies that the low bound of interval 1 is lower than the high bound of interval 2. So just to see it in the picture, this interval 1 and this time 2, where we take the other measurement, have another interval, right? Well, the only thing we can guarantee, and that is a good thing, is that this bound here is actually less than whatever bound this operation, this measurement gives, this high bound here. Okay, this cannot be less or equal. It's always, this is always satisfied. And you can also see it here, how this is derived, right? Because we get first this part of the equation to say that, okay, T1 is always larger or equal to its lower bound. Then we know that T1 is lower than T2, so the other measurement. And we also know that the highest bound of T2 is larger or equal to T2, right? And if we put this together and remove this part, we can derive that low of measurement 1 is less than high of measurement 2. Now let's go back to the protocol, okay, and try to bypass the query phase in our writes in the read impose write consult majority algorithm. So we have we can do two changes. So first, the first change is that we use a different type of timestamp, as I said before. So when a process tries to issue a write operation, what it does is that first measures, it gets its interval clock time, and it picks the high end. Okay. Now, before an operation O that's either read or write is executed before process I can return it, it has to wait until the clock time and the lower bound of its current interval clock is larger than the time of the operation. Okay, so we basically delay. What we do is that we delay the commit of a write until we know that our interval clock has actually passed that time. So if we issue an operation here and we get this interval, then we wait we try to get the current time. The current time is always like this, right? It's always a range. We wait until the lower end of our current time is after the expiration or the highest bound of the timestamp of the operation. Okay, so this is actually waiting. It's actually waiting in real life, in real time. It's not a virtual wait operation. It's actually a wait, and the reason we do that is to satisfy the invariant that, you know, when we issue another operation, this will come after the previous operation has ended. Okay, and by doing so, we can bypass the query phase of the protocol, because every process will use this sort of interval clock to do the same thing. And these bounds are global bounds. They are based on a global measurement, which is real time. Okay, so let's look at the intuition, because this is a bit hard to grasp, I think, if you don't look at the picture. So operation 1 is a write operation, and this is invoked at this time 0, right? At this time 0, we get this interval clock, and we actually cherry pick the high end of that interval clock. That is what we use to commit our operation. Okay, and it's a conservative estimate of what's the time that, you know, it's guaranteed that we have reached, that the real time has reached that point. So we issue a write operation. We actually piggyback this as a sequence number. Everybody receives that, and of course, since it's a write, every other process will commit this write on the shared object, as long as it's higher than, you know, the previous write, because there's always this precedence order when we apply writes. And then they send an acknowledgement, and P1 now doesn't return to client. Okay, that's a difference. Now P1 will wait, and it will wait until its current clock, interval clock, has passed through this commit time. That is the time of the high timestamp of the interval clock that it was issued. So basically, if you see this purple arrow here, this is the time duration that P1 needs to wait until it returns to the client and says this write is complete. And of course, other operations will come after that in real time. So in this case, P2 can initiate, you know, a write, and that write will have its own like timestamp based on the clock of P2. But of course, it's an interval clock. So we have this level of synchronization, right? We know that this corresponds to real time as well. So by using this guarantee, this invariant I said before, we can ensure the following. So if T1 is less than T2, then the lower time of T1. So T1 now, look here, T1 is the time at which we acquire a new interval clock, right? Timestamp. And this has a low and a high end, right? Its low end will be higher than this timestamp. This is this timestamp. Okay, so what do we do really? We actually get an interval from the system, and we wait for that interval to pass until we can commit that operation. Okay, that's what we do. And this means that the real time corresponding to that, you know, operation will elapse during that period. And this satisfies linearizability, because we cannot at the same time, you know, accept changes or initiate something else in parallel, right? By the same process. So we have this invariant that's set here. So this is so this C1 T1 low corresponds to this low end that I talked here, and this is the time that we acquire at process 2 at the issuing of the next operation, that's O2. Okay, and we know that if that's the case, the low of the first is lower than the high of the second. If you remember, we talked about this invariant here, right? This is the invariant we use to order operations in a linearizable fashion. If we don't wait now, let's say we try to implement this first without the waiting part. So we just basically do a write, then this will not work. So we don't do a query, of course, and we don't wait on the write. If we don't do that, then what can happen is that P2, for example, so let's say here, P1 returns operation 1. It doesn't wait this additional time to commit that operation and return it. So it doesn't do that. It returns here, and that gives another process the right to commit another operation while this within this period, right? So let's say P2 is issuing write operation O2, which actually, based on its more accurate interval clock, returns faster, right? It returns before that time. And that is really bad, because if that happens, then we have effectively a violation of linearizability, right? Because the timestamp of O1 will be higher than timestamp of O2. And this is not correct, right? Because O1 was issued and finished before the invocation of operation 2. So if O1 is completed before O2 is invoked, then O1 must be ordered before O2 to have to satisfy linearizability. And if O1 does not wait, then O1 completes before O2 is issued, and there's no guarantee that O1 would be ordered before O2. It might be that it has a lower timestamp. So to summarize the correctness behind this a bit complex algorithm is that it satisfies linearizability by enforcing these delays based on these conservative time intervals that we get. So if we have two operations, any two operations, you can always reason about this and say if operation 1 is read or write and operation 2 is a read, by the same argument as before, O1 is ordered before O2 based on the timestamps. O1 is read or write and O2 is write. Then in that case, we actually go and override something on, override some value, and we have to make sure that it's linearizable. Now, if O1 is completed at T1 by process I, and O2 is invoked at time 2 by Pj, this is time 1, time 2, then we know that if this holds, so if T1 is lower than T2, if this holds, then this implies that their timestamps are also ordered. So the timestamps of the commits of those operations. And since TS, the timestamp of operation 1 is lower than the timestamp of operation 2, the value in O1 is overwritten by the value of O2, and that is fine. And if you see the final algorithm, it's basically exactly the same algorithm. It has very few changes. Okay, so we don't query for writes. Reads are the same. So when we read, on read we just check if all pairs are equal, and in return, this is the first optimization. Otherwise, we issue a write. And the write is one phase, remember. Okay, so what is a write? A write is basically an operation that is trying to send the timestamp, the conservative estimate of a timestamp of an operation to every other process, and waits for a majority. When it receives that majority, then it waits until its current timestamp, which is this here, the lower part of its current timestamp, is higher than the commit time of that operation, basically. And if we are reading, we also return the value we want to read, basically. So that is just an example. Okay, so it's not. I wouldn't memorize this algorithm. What is important to remember from this algorithm is the principle that is the usage of interval clocks. Okay, and I would say spanner is also a very good example. Okay, so for spanner is a bit complicated system. It's a big system. It runs consensus groups. It runs like two-phase commit. So it would take me hours to explain everything. But in the case of spanner, what is nice is that it's focusing on reads. Okay, so everything else takes the normal route. But when it comes to reads, spanner is using these conservative estimates to know that you can actually read the latest value basically based on this interval clock.